Hello, everyone. My name is Ben Gordon, and I am a sophomore at Lebanon Valley College located in Annville, Pennsylvania. And I am a physics major. And I'll throw it over to Adam.
And I'm Adam Rilatt, and I'm majoring in computer science and physics at Lebanon Valley.
Great. And then this is a presentation of our research we did over the past summer, which is the extraction of the Bohr Moulders function from unpolarized, semi-inclusive, deep inelastic scattering data. Just a little bit of background of SIDIS. It's when an electron collides with a proton and emits a high energy photon, which then interacts with a quark in the proton. This quark is then ejected from the proton with some transverse momentum, which it carried before the collision. We noticed that these quarks fly off asymmetrically with some quantized value, which is equal to cos 2 phi. And then there are many ways in which these partons can be polarized within the nucleon itself, within the proton. The focus of our research is to delve into the certain scenario where the quarks are transversely polarized while the proton remains unpolarized. And we can describe this using the Bohr Moulders function. To generate the asymmetry, we need to also include the Collins function. And both of these are transverse momentum dependent functions, or TMDs.
Right. So as Ben just mentioned, the Bohr Moulders function, in our case denoted as little h1 perp, models basically the probability that a transversely polarized quark exists somewhere in the proton with momentum fraction x and transverse momentum k sub t. So we also couple that with the Collins function, which the Bohr Moulders function is the Parttime distribution function, and the Collins function is its respective fragmentation function. We denote that big H1 perp, and we actually combine those into one large structure function, which we call FUU cosine 2 phi. You can see both of those elements within there, as well as a second term, which is the Kahn effect, which deals more with unpolarized Parttime distribution functions and fragmentation functions. So as undergraduate researchers, Ben and I spent some of our time translating those functions into Python code so that we could later run simulations. So as you can see, figure 2 actually shows the Bohr Moulders function in Python, and figure 3 corresponds to the Kahn function, or the Kahn effect.
Okay, yeah, and then looking at figure 4 and 5 now, we can talk about our fits. So we use the SIDIS and electron-positron annihilation data from various collaborations to fit our parameters of the functions for these polarized and unpolarized quarks. From these fits, we can extract how the quarks are moving inside of the proton. And if we're analyzing the quarks moving in a momentum space, this is equivalent to finding the squared average values of the momentum of a quark, which it carries anywhere inside of a proton. And looking at our graphs here, the average unpolarized quark in the first figure, in figure 4, has a momentum kT squared, which is equal to 0.32 giga electron volts squared. And then the polarized quarks have a twice as large momentum as seen in the figure below.
Figure 6 actually represents the actual Bohr Moulders function. On the left, you can see the Bohr Moulders function extracted for up quarks, and then on the right, you can see it for down quarks. It's a function of x, which in our case, x represents the partial momentum carried by those given quarks. So in general, this lines up pretty well with some of the previously researched literature. We can see that as the momentum tends towards 1, saying that the one quark carries the entirety of the momentum of some parton, it tends towards 0, which we expect. It's also entirely negative and has a peak at around x equals 0.25. And then below, for figure 7, we have plots in various binnings of our theoretical and experimental results of our fits, essentially. So, of course, you can see that this is for Hermes data. In our case, we're looking at a proton target, and we're observing positively and negatively charged pions, respectively, for figure 7 and the graph below. So for a lot of these bins, our data did indeed line up with what we saw from the Hermes accelerator. A lot of them, however, did not. And we eventually ended up with a chi-squared per number of points value of 2.2.
And then to summarize here, we've extracted the Boer-Mulders function by fitting data from SIDIS multiplicities, cosine 2 phi data, including the Klein effect and electron-positron annihilation data. The results, as Adam said, are consistent with other extractions of this data or of this function. And in the future, we're hoping to include compass data in our fits and to incorporate the full TMB evolution. We would just like to thank the National Science Foundation for providing a grant to help fund our research. And we'd like to thank everybody who watched this video.